Hi, my name is Tom Kaytt, and I'm an applications engineer for Bruel Kjaer Sound and Vibration. I'm here to talk to you today about using handheld sound level meters in some novel ways to support complex, repetitive, custom test scenarios where simply making a measurement and downloading from the meter may not be the optimal workflow. But first, a little bit about me. I joined Bruel Kjaer 4 years ago with about a decade of professional experience in noise and vibration work, primarily in commercial acoustical consulting. My work these days consists primarily of product training and customer support for our S&V customers across the continent. Being located in Palm Springs, California, however, my focus is primarily on the west coast of the US. I've been a user of B&K sound level meters since I was first handed one in college back in 1999, and I'm happy to share some of that experience with you today. Here's a quick overview of what we'll be reviewing today. First, a quick look at the evolution of sound level meters over the past 75 or so years. Then, I'll introduce you to B&K's current lineup of handheld sound level meters. We'll follow that up with an introduction to the Sound Level Meter Open Interface API. And finally, I'll present some demonstrations of methods that can be used with these meters' connectivity and remote capabilities to generate more effective and rapid testing applications in your job. The earliest sound level meters will seem primitive and massive by today's standards. This General Radio 759B from the early 1950s was the Cadillac of its day. Selectable acoustic weightings, fast and slow time responses, and all that at only about 20 pounds. Here we see a similar unit from a bit later on. Notice there's a second technician needed to operate the octave band filter so that a spectrum can be measured and recorded by hand, one band at a time. These were marketed at the time as handheld devices. Through the 60s and 70s, B&K released a string of handheld analog sound level meters with significantly reduced weight and size. New features included max hold and impulse measurements, as well as directly attachable and eventually integral octave filters. At this point, though, any more automated use than simply an audio output was relegated to much more expensive and massive laboratory equipment. This began to change in the 1980s with the introduction of the 2230 line of sound level meters. These microprocessor-controlled devices were capable of custom software sets for different types of tests, onboard memory for electronically saving measurement results, and octave filter sets that could be remotely controlled from a strip chart recorder to allow automated measurement of a full spectrum, albeit still one band at a time. Things changed in a big way moving on in the 1990s to a lineup of fully computerized meters with LCD screens for advanced configuration and setup and for viewing data. For the first time, we were gaining the ability to measure an entire octave spectrum simultaneously on board a handheld analyzer, and the computing power of the 2260 meter made it possible to measure vector sound intensity using a 2-channel, 2-microphone phase-matched probe arrangement. The 2260 sound level meter remained an industry standard for many years, but eventually posterity must yield to technological progress, and the B&K 2250, still our flagship sound level meter, was released in 2004, followed by its 2-channel counterpart, the 2270, in 2009. The increased computing power to measure more parameters of sound than ever before, the flexible data storage handling, and the advanced application software like FFT analysis and building acoustics measurements have made this an incredibly popular sound level meter over a very long lifetime. And finally, after many years, we have a new next-generation meter to share with you. This is the 2245, which we first released in 2019. This is a lower-cost, high-value meter designed to give you the same accuracy and dynamic range you've come to expect from the 2250 in a smaller, easier-to-use package and at a fraction of the cost. We'll talk more about this meter in a bit. Now, before we dig into some advanced test automation strategies, I'd like to give you a quick overview of the capabilities of our currently available sound level meters. We'll start with the 2250 and 2270. The 2250 and 2270 sound level meters are capable of measuring broadband sound levels as well as octave or 1/3 octave spectra simultaneously. They're capable of measuring vibration, using CCLD accelerometers plugged into their rear input sockets. And with a 2270, they can make two-channel measurements simultaneously, which is very useful for doing indoor-outdoor measurements or measuring sound and vibration simultaneously. And finally, 2250 and 2270 come standard with access to the open interface for programming your own applications. With additional software options, these meters can be configured to record wave audio files, to log decibel levels versus time, to compute FFT narrowband spectra, to measure reverberation time and building acoustics insulation parameters, and on a 2270 with a sound intensity probe to make vector sound intensity measurements. Data storage on the 2250 and 2270 gives you the option to store data on an internal hard disk or on an inserted SD card or USB thumb drive. Connectivity includes an analog voltage output signal, TTL trigger input, remote control via LAN or USB Wi-Fi adapter, and control via the REST interface Open API. And the 2245 as well, though it is a lower cost meter, is also very capable. Its most basic package includes only broadband analysis, but options can be added to include octave and 1/3 octave analysis, MP3 audio recording, logging level versus time, and access to the open interface for remote control and data readout. Data storage on the 2245 utilizes a 16 gigabyte internal disk, but also gives you the option to automatically backup save data to a USB-C thumb drive or to a network accessible file server. Connectivity features include an analog voltage output signal and remote control via USB LAN adapter or integral Wi-Fi using the iOS phone app or the Open API interface. The integrated Wi-Fi on the 2245 is designed to work seamlessly with our iOS apps for remote control and annotation. These apps are not required to use the meter, but they do open up a suite of additional features that can save you time and effort in documenting and organizing test projects. The physical I/O for the 2245 is incredibly simple, using only a single USB-C connector for power, data, and analog output. The built-in Wi-Fi can be used either as a hotspot for connecting your phone to the meter, or in a client mode so you can connect the meter to an existing local network. Bluetooth onboard the meter also is useful on the iOS app to quickly connect your meter to the local Wi-Fi. Okay, now that I've gotten the sales pitch out of the way, I'd like to introduce you to the open interface architecture for our sound level meters. We'll be focusing on the WebXI API for 2245, but the interface for 2250 and 2270 work in much the same way. The sound level meter APIs are based on REST communications architecture, which is compatible with popular programming and analytical platforms, including but not limited to MATLAB, Python, C#, Excel, NI LabVIEW, and the list goes on. REST, or Representational State Transfer, is a web standard system that allows pretty much any programming environment to interact with the device over network-based HTTP commands and responses. You can use this interface to read live data from the meter, to start and stop and save measurements, and to configure measurement setups. I'll note at this time that while I'm going to show you some real coding examples, I am definitely not a skilled programmer. The possibilities are much larger than the rudimentary demonstrations that I'm going to show you here today. The WebXI protocol, which applies to both 2245 sound level meters and our LANXI data acquisition hardware, is fully documented on our GitHub site. Feel free to visit github.com/hbkworld. The site also includes documentation specific to the sound level meter and a selection of real coding examples to help get you started. Let's start with a very simple example. Both the 2245 and the 2250 are capable of mirroring their display over a network connection. This can be very valuable for your remote demonstrations like mine today, or to give your stakeholders real-time access to meter data while it is in use. In either case, you just need to enter the IP address of the meter /display from any web browser. For this demonstration, I have a 2245 connected to my local office Wi-Fi and a 2270 using a wired Ethernet connection to a network switch. Here's the display of the 2245 on a live remote display. You can see me here navigating the meter and making a simple measurement. This is a 15-second measurement showing the SPL logged once every second. For a 2250 or 2270, it works much the same way. But we aren't limited to simply viewing the screen remotely. We can also control it remotely too. For the 2245, we can easily connect to the meter, view live feedback, and control and save measurements using the phone app. The app makes it easy to make text, voice, photo, and video annotations, which are immediately stored to the meter alongside your acoustic measurement data. Remote control of the 2250 and 2270 are most easily done from a web browser. Using the option to view and control instrument, we gain access to a virtual touchscreen and keypad that allow you to control the meter exactly as if it was directly in front of you. Now I know that we're all living in the age of big data, but I also know that sometimes all people need out of their test is a rapid way to get the dB level of their system measured and embedded into a larger set of test data. In some cases, the ability to take a DC voltage proportional to the SPL can be just the simple tool for the job. For this demo, I have the analog outputs of both meters connected to a secondary data acquisition system. The 2245 requires a USB-C to audio adapter. Here I am, showing the raw sampled voltage coming out of each meter, which we know corresponds to the A-weighted decibel level. Just having the voltage level isn't terribly useful, however, so a quick adjustment to define the sensitivity of each channel, 20 millivolts per dBA for 2250 and 10 for 2245. And we now have signals reflecting the actual dBA of each signal. I have a customer actively using 2245s in this exact way right now on their production line. Every one of their units goes into a test chamber where it is tested for various mechanical and electrical performance goals in a LabVIEW project, and the dBA value is captured right alongside all that other data without the need for a high sample rate data acquisition device as the primary data logger. A simple analog voltage, however, can only give you one number at a time. Let's dig into the power of the open interface to get a little bit more out of it. Here, I'll show you a way to pull the live SPL octave spectrum into an Excel worksheet. Now we've already seen how we can view the 2250 display and control it from the web browser. Now I'm going to dig down a bit deeper to explore what the API has to offer us. When I add /remote/data to the meter's address, I am greeted by all of the available data being served up from the meter. I'm interested here in finding the fast-weighted, real-time 1/3 octave spectrum for this meter. I happen to know that the command starts with CPB, which stands for constant percentage bandwidth, which means octave bands, and I'm going to search by that to find the correct command for this function. Here it is, CPB LACZF. It comes with a table of values expressed as decibels times 100, and that's mainly to eliminate the need for decimal points in the raw data. We can find the data we want similarly on the 2245. I'll add webxi/application/slm/outputs to get the active list of data. Here, the best selection is going to be CPB LZF 250 milliseconds. Now I'll go to an Excel spreadsheet that I have prepared for this very purpose. I have two web data sets defined in Excel, one for each meter. The query populates dynamic table columns, which I'm bringing into my report page and dividing by 100 to get the correct decibel scale. Now, anytime that I press my update button, I get an update of the spectrum from each meter at the time that it was pinged. I actually built this demo explicitly for a customer who wanted to use their sound level meter to tune an architectural sound masking system. With this system, they were able to monitor live noise levels from their system while 100 feet or more from the sound level meter, making adjustments to the noise generator EQ and overlaying the meter's results with their pass-fail criterion. Now, with a little bit of initiative and coding know-how, it's easy to surmise how this entire process could be automated, where the noise levels from the sound level meter are fed back into an equalizing algorithm and in a positive feedback routine will converge on the optimal noise spectrum measured in the room. This final demo is a bit more bare bones. Here, we're simply going to create a loop to continuously measure the dBA level using a very basic Python script. Not counting comments, this entire script comprises only 8 lines of code. We import the appropriate function libraries to parse the JSON responses from the meter. We print out the results and time the repetition. We identify the IP address of the meter, and we create a simple looping query that captures the dBA level once per second. Now, perhaps this example borders on trivial, but the implications for potential on making something like a custom noise monitoring system or an active quality control system are massive. So, in conclusion, I hope you feel a little bit more familiar with what our sound level meters have to offer and some idea of the legacy that exists behind them. With the release of our 2245, we've opened the door to a new generation of sound level meter focused on creating not just a powerful analytical tool, but a more useful and user-friendly test instrument than ever before. And finally, I hope that you come away from this session with some grand ideas for how that sound level meter you may have on the instrumentation shelf could become a more integral part of your practice, giving you access to better data faster. Thank you very much for your time. I hope you found this to be useful, and if I can be of any assistance with your noise test application, please feel free to reach out to me at any time. My contact information is here on the screen.